Okay, so we're looking at the Unit 4 simulation on intermolecular forces, and we want to look at some of our findings from the simulation, make sure we got everything. So one of the most important things is when we're talking about any van der Waals forces or any intermolecular forces, they really come down to attractions between oppositely charged ends. How polar a molecule is will determine the strength of that attraction between the opposite ends. You know, we talked about calculating dipole moments, how the the polarity of the bond varies with the differences in electronegativity. So all that stuff that we talked about before factors into the strength of that attraction. But notice that we're depicting those attractions with these dashed lines between molecules. So these right here are the bonds holding the molecule together. Those are the covalent bonds. That is different from what we're looking at with intermolecular forces. So notice the partially negative end attracts the partially positive end. That's where the connections appear. We do not get any connections between the positives. So that's one important thing to note. The other thing is we do get attractions between these molecules, the nonpolars, and again, these are going to be weaker attractions because these are not permanent dipoles, but because of a shifting in electron density, randomly, we have the momentary dipole and then an induced dipole as a result of these molecules getting close. So there are some attractions between the nonpolar molecules as well. You may have even seen some attractions between the nonpolar and polar. Again, those would be dispersion forces attracting them. But again, we look at a comparison of this attraction versus this molecule's attraction for this one. This will be a stronger attraction between the partially positive and the partially negative end versus the attraction due to the just momentary shifting of electrons in the nonpolar molecule. Okay, so that's what we should have come up with in the first. When you're drawing your HCl molecules, again, you should have drawn something similar to this, except with H as the positive and Cl as the minus, and then dash line between the two. When we are looking at the second simulation, again, this is just looking at differences in polarity. So, if there's only one, like if it's a chain molecule, like a hydrocarbon that happens to have a polar region, well, there's some attraction between those oppositely charged parts. There's some attraction due to dispersion forces between the rest of the molecule, but we'll notice that it is the more places where there's those partially positive, partially negative charges, the more difficult it's going to be to separate the molecules. And so that means that their intermolecular forces are going to be stronger the more polar the molecule. So again, it can be a scenario like this in this depiction where there's multiple locations of partially positive and partial negative charges, or it can be, just again, if I had small molecules but had a very polar bond, then that also would result in a stronger attractive force. All right, so moving on to the next simulation, we are looking at the nonpolar molecules versus polar molecules. So again, we kind of already mentioned this when we looked at those interactions on the very first simulation, but the permanent dipole, the permanent positive and negative, is going to result in a stronger attraction between these particles and stronger intermolecular forces, which again will be evident in the properties of the substance that we can observe, like when we're talking about boiling point and separating the molecules. What temperature will that happen at? Again, the stronger those attractions, the higher the boiling point, lower the vapor pressure, etc. Okay, so then moving on to the next simulation where we're looking at dispersion forces. Dispersion forces only. Again, small molecules, any molecules, there's going to be some attractions between them, very weak attractions. But the larger the molecule, again, the more, in this case, there's more places for contact between the two, for attractions between the two. Also in larger molecules, we tend to find more electrons, and the more electrons mean that they're more polarizable. We can see a larger shift in temporary polarity, right? So if all the electrons end up on one side of the molecule versus the other, that can be a much stronger temporary dipole than when there's fewer electrons. But the shape also, again, how the molecules are able to make contact with each other, that's what this part of the simulation is getting us to look at. So obviously, like when we have this, the circular, it can only make contact in a couple of spots versus, when we have the linear, they were able to contact, more, have more places of contact. So that's what this was kind of getting us to take a look at. So again, we're looking at nonpolar molecules. It's not just as cut and dried as, oh, it's nonpolar. There's only dispersion forces. The larger the molecule, the more contact that we have between the molecules, the stronger those attractions will be. So we have to keep that in mind and not just think of it as a, dispersion are weak and always weak. Next simulation, we are looking at hydrogen bonding. So again, when we start this thing out, notice the hydrogens, or the white, they're partially positive. They attract to the partially negative on oxygen in the neighboring molecule. Notice that as we cool these down, take it off slow motion, as we cool them down, again, we talked about the fact that particles will move slower, and they start to align themselves and slow down and stick together because of those attractive forces. And likewise, when we heat them up, they move faster, and then obviously can then overcome those attractions because their kinetic energy is greater than that attraction for the neighboring molecule. The thing to keep in mind, and this is very centrally important, this comes up in the study of organic chemistry as well, biological molecules in addition to water interactions, but these dashed lines appearing, those are the hydrogen bonds. The hydrogen bonds are not the bonds between hydrogen and oxygen themselves. So that's very important to pick up from this simulation. Another simulation is, this one we're looking at the changes in states of matter. So if I have a weak attraction, notice that as the particles are heating up, they spread apart very quickly. Whereas if I have a strong attraction between the particles, actually, now let's rewind this, do it again. So again, this is representing heating of particles with very strong attractive forces. Well, again, even though the particles have more kinetic energy, if that kinetic energy is not enough to allow them to free themselves from the attractions of the neighbors, they're going to stay stuck together. And so again, when we look at the ramifications of the strength of attractive forces on things like boiling point, vapor pressure, etc., the stronger the attractions between the particles, the more difficult it's going to be to separate them, which means it's going to take more energy to separate them, which means they're going to do so at higher temperatures. All right, so that is some of your findings from the simulation. Again, we can kind of see the same trend with, showing the polar and nonpolar molecules as we heat this up. And notice the nonpolar break apart first, because once they have enough kinetic energy to overcome those weaker attractions, then they come apart. All right, so the last section is this review of types of intermolecular forces. We already looked at the boiling point differences between the polar and nonpolar molecules. When we look at the comparisons, so HCl to H2, again, we compare, we can kind of think of that as an example of what we saw in the simulation. HCl is a permanent dipole, so that would have dipole-dipole forces acting between it, compared to H2, which is nonpolar. So we'd predict that HCl should have a higher boiling point because of those stronger attractive forces between the particles. When we actually look up HCl, it certainly does have a higher boiling point. When we compare hydrogen to chlorine, so notice the hydrogen has a low boiling point compared to chlorine. Both of them are nonpolar molecules, so they only have London dispersion forces acting between them. But again, we notice that correlation with the larger the molecule, the stronger the London dispersion forces. And again, even if we're talking about a polar molecule, if we're comparing two polar molecules, the larger the polar molecule, the stronger the attractions are due to London dispersion forces. And we can have a cumulative effect as well on the attractive forces. So again, you can there's London dispersion forces acting between all molecules. That's the only thing going for nonpolar molecules. But again, the larger the size, and really it's not the mass itself, but rather more electrons with the larger atoms, larger molecules, then that are more polarizable and then cause those stronger temporary dipoles and allow the particles to stick together more strongly. Again, if we look at down here just to compare, again, if we look up HF, those molecules would have hydrogen bonding between them. Again, it's not the H to F covalent bond that's the hydrogen bonding, but it's the H, the partially positive charge on an H, attracting the partially negative end of a neighboring HF molecule. So that's similar to what we saw in the H2O simulation, or the H2O part of the simulation, where the H's were attracting the O's in neighboring molecules. So because that is a very strong attractive force, we see that the HF has the highest of all the boiling points of the substances that we've looked at here. There is a limitation to, again, if I'm comparing something that has hydrogen bonding versus a very gigantic molecule, then we might see something with very, very large numbers of electrons and very large dispersion forces, or high, strong dispersion forces, can in fact have stronger attractive forces than some very tiny molecules with hydrogen bonding. So you do need to pay attention to the size of the molecule and not just the, is it dipole-dipole or hydrogen bonding or dispersion forces. So that's it for worksheet, for this worksheet for the simulation. And again, we'll be doing more comparisons with the attractive forces in the future.